Hey there, this is another edition of Kung Fu Physics. We're working through mechanics problems on the Physics GRE, the practice exams. I want to do number 26 off of the 2001 exam. Looks like this. Let's start right into it. Now, a quick look at the answers shows that they are all going to have similar units. It's just multiplied by some type of constant that's going to determine the difference in the answers. So, okay. We start into the problem, number 26. A thin, uniform rod of mass big M and length big L is positioned vertically above an anchored frictionless pivot point as shown above, and then allowed to fall to the ground. With what speed does the free end of the rod strike the ground? Now, first things first about this problem is, as in any physics problem, there are many ways to solve it. As in any physics GRE problem, there are fast ways to solve it and not so fast ways to solve it, and you always want the faster ways. In this case, I have to say, after going through a few of the various ways to solve this, I would say there's probably at least 3 fast ways to solve this problem. So, challenge to you is think of some of the other ways to solve the problem other than the way that I'm going to present it. The way I'm going to present it is the way that I actually solved the problem and the first thing that came to my head, and it works fine. But to be honest, I like the other 2 solutions too. And for that matter, I like this problem in that there are some creative ways to solve it. So, the first thing that popped into my head when I did this is conservation of energy. So I know that when the situation starts and this thing is standing upright, it's got potential energy centered at the center of mass. Now, just before it smacks the ground, I know it's rotating with some omega, and the way I see it, and I'm giving you a clue here as to a different way to solve this problem, and a good way to solve the problem. But the way I see it is that all the energy is just a rotational energy. I'm not looking at this as a kinetic energy, even though center of mass is clearly moving, and a rotation. It's totally legit to look at it as just a rotation. All of the energy is kinetic energy due to a rotation. Omega is turning, the rate that this thing's turning, and this thing is turning like that. It's all rotational kinetic energy. And so that's how I'm going to solve the problem. Like I said, work out the other ways and think about it. Think about what's the fastest way to solve the problem for you, and what's the best way to solve the problem for you. So basically, I want to do energy initial equal to energy final, and the energy initial is just going to be the mass of the rod times gravity times where the height of the center of mass, and that's 1/2 of the way up the rod here, right? So that's what I get on that side. Now the rotational kinetic energy is going to be 1/2 I of the rod times omega squared. And so my thinking in this problem was I want to get omega as fast as I can. If I know what omega is, I can get the velocity at any one point due to the relation, the velocity, I guess tangential velocity of any of those points is going to be omega times d, being the distance out to those points. So if it had asked for the velocity at the center, I could have solved that. Another clue to the one of the other ways to solve the problem. It wants this velocity, this tangential velocity, but I know if I get omega, then I can have the velocity, because you just divide by the length or whatever. So this is the other thing you have to be sort of careful about. When you do it this way, you are not, all the rotation is not about the center. You're taking it about the pivot point. You're saying all of the kinetic energy, if I take it from this end, is going around that axis. If you do it around the center of mass, and now I've totally blown how to do it the other way, you have to consider the translational velocity. That's the other way to do it, is considering two terms here, both the rotational kinetic energy and the translational kinetic energy. You'd have to add those two in. But if you do it this way, you can just do it this way. But the catch is the moment of inertia of the rod has to be about this end. And so you don't actually have that. A rod about the end, you don't have that given by these equations. You just have the center of mass. It gives you the moment of inertia of a rod is 1/12 mL squared. And the distance in our case out to that, or no, that's right, L squared. We'll use L squared. And then I need to use the parallel axis theorem because I'm going about this. So I kind of treat everything like a point mass. I add in both the original moment of inertia for a rod about center of mass, and then I treat everything like a point mass. That's the way I see it in my head when I do parallel axis theorem calculations. And so then I get mr squared. In this case, r is the distance out to the center of mass, which is L over 2, right? So my I is going to be 1/12 mL squared plus m times L squared over 4. I've squared everything there already. Okay, so you do the algebra, and I'm trying to speed this up a little bit. 1/12 plus 1/3 is 4/12, which is 1 over 3. So I get that for my I. Now again, that's the moment of inertia of the rod about the end. And that's what's different. Okay, so go back up here and we start plugging this junk in. And we want to solve for the omega. And this stuff drops out pretty quick. You get 3GL equals L squared omega squared. Now remember what I said. The velocity tangential equals omega times L. And I'm taking it as L because we want the velocity all the ways out at the end of the rod. So you use the full length there. It means that omega equals velocity over length. And omega squared equals V squared over L squared. So 3GL equals, the L squareds cancel, and I get V squared, and V equals square root of 3GL. Okay, so that's it. That's the way I originally did the problem and thought to do the problem. Check our answers there, of course. That is leading me to answer C, square root of 3GL. And there are other ways to do it, and the most obvious one would be not lumping everything into a rotational energy, but as I said, using a translational energy of the center of mass, because the center of mass is moving down, plus a rotation. And that's one way to do it. The other way to do it is using some very simple calculus, using a differential for the mass. And I saw that posted in one of the solutions online, and I can't remember exactly how it goes. I wouldn't want to go there just because for me this type of approach, one of the other two ones I've suggested, seems a little more bomber proof for me. Not that my calculus is bad, but you know, I probably just wouldn't go there. I wouldn't think that on the physics GRE, but it's worth looking at the problem that way as well. It's a very good solution. I kind of liked it. So that's it for this one. This is number 26 off the 2001. Thanks for watching. See you next time.